periodic table trends. So the periodic trends are mainly a result of the atom's positive nucleus's ability to attract the negative valence electrons. How strongly does that positive nucleus pull and attract the negative valence electrons? So there are three atomic periodic table trends that you need to know and be able to define. So when we talk about the atomic radius of an atom, it's basically the size of the atom. And when you move across the period left to right, the atomic radius tends to decrease. So the atoms become smaller as you move left to right. Down a group, top to bottom, the atomic radius tends to increase. The atoms tend to become larger. Now another term, you need to get the definition memorized, is the electronegativity. Symbol is En. The electronegativity values, they describe the ability of an atom to attract or pull the electrons in a bond towards itself. So across the group, moving left to right, the electronegativity value tends to increase, meaning it attracts those electrons more, so stronger attraction. So stronger attraction. Whereas down a group, the electronegativity values tend to decrease. So there is less attraction or less pull on those electrons in a bond. The third term here is ionization energy, the IE values. This is the amount of energy or work to remove a valence electron from an atom. So as you go left to right across the periodic table, the ionization energy values tend to increase, which means it's harder to remove an electron. Takes more work. Down a group, the ionization energy value tends to decrease, which means it becomes easier to remove that electron. And our last and final term here is metallic character. Metallic character is the ability of an element to exhibit the properties of a metal. So when you move left to right across a period, the metallic character tends to decrease. Whereas down a group, top to bottom, the metallic character tends to increase. So take a look here. Now you can memorize the trends, or you can use your table S to figure these out. So let me just move this up a little bit. So I'm looking at period 2. Period 2 starts with lithium, and group 17 element is fluorine. So the first thing I'm going to compare is their atomic radius. So I'm just going to write AR, and I'm going to write AR. So lithium, when you turn to table S and you look at the size or the atomic radius of a lithium atom, it is listed as 130 picometers. Whereas when you go to fluorine, element number 9 on table S, the size of the atom is only 60 picometers. So as our general trend, 130 moving towards 60, when you go left to right across a period, we tend to see a decrease in the atomic radius. Okay? And then we take a look down a group where we have lithium starts the alkali metals down to francium. We already know that lithium's atomic radius is 130, and when you look on table S and find francium's atomic radius, it is 211. So we go from 130 and moving down a group to 211. As we go down a group, okay, the atomic radius increases. So we see an increase in the atomic radius. The next term was electronegativity. So when we go to table S, so I'm going to write En here for electronegativity. Lithium's electronegativity value is 1.0. And when you move across a period, fluorine's electronegativity value is 4.0. That should be a 4. So as you move left to right across a period, we see an increase in the electronegativity values. Let's look down a group. When we look at lithium down to francium, francium's electronegativity value is 0.7. So it's less than 1. So we go from 1 to 0.7. So when you move down a group, the electronegativity values decrease. So we see a decrease in the electronegativity values. Our next idea here was ionization energy values. So I'm going to put IE here. So when you go to table S and you look up lithium, its ionization energy value is 520. And when you move across a period and you look up fluorine's ionization energy value, it's listed as 1,681. So as you move left to right across any period, 520 to 1,681, we tend to see an increase in the ionization energy values. Harder to remove an electron. Down a group, lithium down to francium. So lithium, we already know its ionization is 520, and francium's ionization energy value is listed as 393. So when you move top to bottom down any given group, the ionization energy values tend to decrease. So we see a decrease in the ionization energy values. Now, on our periodic table, right, I have the little stair step, and so I'm just going to shade these particular spots with a little bit of yellow. So where I shaded these guys in yellow, they represent metalloids. And sometimes I short form them as SM for semi-metals. And then I'm going to try to do, I guess, a lighter blue color here. And so now, with a little bit of lighter blue, my lighter blues, these are my nonmetals. And now I'll choose a lighter color here, maybe a pink. And I'm just going to start shading in here. On here with these, and so my pinks, these would represent metals. So sometimes doing it this way, it helps us see this. So if I take a look at group 15, okay? So group 15, I start off with a non-metal, then go metalloid, and then metal. So as I go down a group, any given group, okay, and it's easier to see from groups, 13, 14, 15, 16. It's much easier to see it in these particular groups. But as you go down any group, down the periodic table, you go from non-metal to metalloid to metallic down these. So as you go down any group, we see an increase in that metallic character. And so if I look at, now if I go across a period, so if I go left to right, I've got pink, metal. Now I hit a yellow, metalloid, and now blue, nonmetal. So as you move left to right across any group, you go from metal to metalloid to nonmetal. So as you go left to right across any group, there is a decrease in the metallic character. So your most metallic elements are lower left. So this area, region here, these are your most metallic character. Top right, least metallic. So francium to fluorine, they represent the opposites. Your most metallic, they are large atoms, and they have low electronegativity, so low pull on electrons in a bond, and low ionization energy, very easy to give away electrons. Where top right, we have our least metallic, so we have smaller atoms, high ionization energy, so they pull really hard on electrons in a bond, and they have high ionization energies, very hard to remove their electrons. Using these ideas, answer the questions on page 71.